Welcome back, ladies and gentlemen. We got a big one here for you. This is a video, obviously, about forces in two dimensions, but there's a lot that is going to be packed into this one. We're going to be dealing with forces as vectors. We'll list this stuff. Forces as vectors. You know what a vector is. We're going to be looking at normal force because it's pretty cool, and it's not as straightforward as sometimes people think at first. Normal force. We're going to look a little bit about weight, because, well, again, we have to figure that out. It's a simple idea, but you got to be able to work with it. And finally, what's going on when a surface is inclined? Inclined surfaces. So on top of all of that, we are going to see in action Newton's second law a lot. Newton's second law. This will be a bunch of stuff that makes Newton's first law evident. But we're not going to do too much with Newton's third law in this particular video. It is happening, unavoidable, but we're not going to dwell on that one. There's already so much happening. Here we go. First, I would like to talk about a situation where we could have a, let's say, a little sled that could be used to just like sled down a hill in the snow, and it's just kind of sitting here on level surface, and it's just sitting there for now. We know some information about this. Let's call the sled's mass 5.1 kilograms. It's just there all by itself. Okay, now we have to ask ourselves about forces. We're going to do the free body diagram thing here. And so, well, what are the forces acting on this thing? Well, there is weight. So we see that coming up right away. And there is a normal force. Now, a normal force is a force of support from some surface that is perpendicular to that surface. There's our normal force. This is not a proper free body diagram, obviously. Let's do that. So, sled dot. And to start off, I want the free body diagram to have a coordinate system in x and y direction. That does matter. There's positive y. Let's do positive x right there. And that's pretty traditional. Weight is downward. Okay. And normal force is upward. Now, the question is, why am I drawing them equal length? Those two arrows should be equal, and they are in opposite directions. Are they a force pair? Is this third law happening? No, because they're two forces that are acting on the same object. So it's not a force pair in Newton's third law kind of thinking.
Octavio Cordon, please report to the reception desk or dial the operator. Octavio Cordon, please report to the reception desk or dial the operator. Okay,
sorry about that. Continuing. Why am I making sure that I draw those equally? Well, the reason is this sled is sitting here. Newton's first law, it's going to keep doing what it's already doing. It's lazy. It has inertia. And it's going to do that until some unbalanced force acts on it. Well, reverse that thinking. I can observe that it's staying there. Therefore, I know that all forces acting on it are balanced. So I know those are balanced. Here's a proper way of looking at that. I have sum of forces in the y direction. And I can observe that there is zero acceleration in the y direction. This thing is not accelerating upward or downward. I see that. So I know that, well, sum of forces is one way of kind of looking at net force, but I'm only looking in the y direction here, vectors, right? Well, that would be mass times acceleration. I observe zero acceleration, so I observe zero net force. But those forces are my normal force in the positive direction and my weight in the negative direction, and that sums to 0. Okay, that tells me normal force equals weight. Excuse me. Well, that's interesting. My goodness. Okay, sorry about that. Normal force is equal to weight. Is that always the case? We're going to see whether that is. But we haven't sort of defined the weight thing. Normal force we have, it's perpendicular to the surface, always. Perpendicular to that surface that's providing the support. But what's up with the weight? Okay, well, imagine an object in, let me use a different color here. Imagine an object in free fall. Kind of doing this off on its own thing. Something in free fall. The only force acting on it is that of gravity. So there's weight pulling it down. And it will be accelerating. And Newton's second law tells us that the weight is the only force acting on it, so that is a force, and we have mass times acceleration. But I'm going to rearrange this. Acceleration is really the effect of the force. This is the result. It's what happens when there's a force acting on it. There you go. Now, excuse me again. This acceleration, if that's the only force acting on it, that will be equal to the acceleration due to gravity. Ha! So I can rewrite weight to be equal to mass times little g. M little g. There we go. That doesn't change what's going on right here with normal force. I just wanted to point that out, that weight is calculated as mass times acceleration due to gravity. Okay. So what have we seen so far? With an object that is stationary, it will remain so forever until acted upon by an unbalanced force. Since we can observe that it is staying there, no acceleration, we can infer or determine from that all the forces acting on it are balanced, and therefore the single force down is equal to the single force up. What about forces in the x direction? Well, that's easy. Sum of forces in the x direction is 0, because there are none. There are no forces in the x direction in this situation. All right. Could we figure out the weight of the object, and therefore could we figure out the normal force? Yes, we can, because that's an mg. And so m is 5.1 kilogram. G is 9.8 meters per second squared. Multiply. Handy dandy calculator. Times 9.8. Boom. Right, it really rounds to just about 50 newtons. And so therefore I also know the normal force is providing 50 newtons of support force. Excellent. Sorry if that was off the screen. There it is. Okay, well that's a simple situation. I'm going to change it. Of course we are, because that's what we do. We can make things as complicated as we can. No, not really. Actually, that's the opposite. Physicists, what we really like to do is simplify them as much as we can. But we have to be able to simplify a complicated situation. So I'm going to change the situation here. We have our surface of snow or ice. We have our sled. Little curly up in the front. Okay, there's our sled. Now, the change is there's going to be a kid pulling it. So there's some rope tied to the front of the sled. Rope to the kid's hand. And so there's kid happy playing in the snow. Oh, so what's the same? Well, the mass of the sled is still the same, right? Mass of the sled is the 5.1 kilograms. But we have forces acting on the sled. There is still a weight to the sled. That hasn't changed because that's mg. There is still a normal force, but I'm not sure how long to draw that guy because it's not quite so simple. There is this extra force here along this rope. Okay, and so, oh, it's at an angle as well. Oh my goodness. We have an angle theta to the horizontal. So some information. We have the mass, which is the same. The angle theta, let's call that 38 degrees. Sounds reasonable. This force that is applied to the rope at that 38 degree angle, let's call that 17.5 newtons. It's not a very big force. That's the force that a child could easily generate pulling a sled. An icy surface, so that we're going to say there's no friction taking place between the sled and this surface. No friction. Sometimes that no friction description is given to you directly. Sometimes you'll see the word smooth as a description, and when they say smooth, you can assume it's a frictionless, ideal surface. All right, so what the heck? Check this out. We need to make our free body diagram. So I'm going to do this first with coordinate axes. Let's do Y, let's do X. Still just concerned with the sled. Okay, now I'm going to draw in my weight. That hasn't changed. I'm gonna do this differently. I'm gonna first draw this in. This is a known, so I know that. That is there. Force applied. Now when I do a free body diagram, I don't want to break anything up into X and Y components in this diagram. I want to do that separately. And so off to the side, I can just kind of do dot, I can do F, and I can, watch this, imagine X and Y components. This guy is F in the X direction, and there's my angle theta. So this side of that right triangle is equal to F cosine theta. This component is the Y component, and it is equivalent to this side of the right triangle, so it's opposite of the angle, so this is F sine theta. I'm going to want that information later, but I don't put those components here. And really the only reason is that I can imagine is it prevents a lot of clutter in this diagram. But more specifically, the AP exam doesn't want those components here. They want just the forces, not components of forces. And they'll probably even tell you so. Okay, now I'm going to pencil in the normal force. Watch this. The normal force used to be equivalent to the weight. Is it still equivalent to the weight? I'm going to draw it as long as the weight. About like that. Okay, it used to be there. Yeah? That used to be the guy. Well, is it still like that? What do we know about the sled? We know that it is not accelerating upward or downward. The acceleration in the Y direction is 0. So we know that, just like before, if there is no acceleration in the Y direction, then the sum of forces in the Y direction have to add up to 0. Cool. But what are those forces in the Y direction? There is a normal force upward. It is still present there, at least we assume so for now. But there's part of this force F is vertical. I have to include that component in this list of forces. And it's upward, so it's going to be positive. So this is F in the Y direction. And then also weight in the downward direction is 0. Okay. Did the weight change? No. That is unchanged. And we added this force. So therefore, the normal force must have changed to compensate. Okay, so it's going to kind of go like this. What was the weight? The weight was 50 newtons. And how big is this Y component? Well, the Y component, I'm going to look at this. F is 17.5 newtons. And sine of theta. Well, theta is 38 degrees. Sine of 38. And so my Y component, turns out, is 10.8 newtons. So there, 10.8 newtons. And, look at this. I'm able to find the value of the normal force, the new value. what is that normal force's value? I just move everything over, and I'm going to get 39.2 newtons. It changed. The normal force used to be 50 newtons, and now it's less. It's 39.2 newtons. And here's your thinking. Part of this pull from the child is acting to support the weight of the sled. The Y component is acting to help support the weight of the sled. Therefore, the ground does not have to support as much. And so the ground provides less support. So the normal force there is now different. It is reduced. Okay, that's pretty interesting. But, well, now what? Well, that's all well and good, you say, right? What was important that we've seen so far? Let's go back to this stuff right here. We need to hit this and nail this right here. Have we seen forces at vectors? Well, yeah, we're going to see some more. How about normal forces? Yeah, and we realize now the normal force is not always equal to the weight. It is not necessarily, but it is a support force from the surface. We've looked at weight. That's an easy guy. That's just mg. Inclined surfaces. We've seen Newton's second law in the first law. Inclined surfaces. That's what we have to investigate. So, here we go. I'm going to change this up yet again. What's the kid going to do? He's going to pull that sled to the top of a hill. And let me go back to the purple. He's going to get on the sled, and he's going to want to slide down the hill. I mean, that just makes sense. I would too. And then I would crash and bust my other shoulder. So let's not do that. Let's let the kid play. Kid will have fun. So we're going to have the kid on the sled. Kid having fun, right? Going down the hill. All right. So what's the situation? Oh, he might have like a rope tied to the front for a little bit of control. What is our situation in this instance? Well, there's something we need to know. How steep is this hill? Do we have an angle here? It's angle theta. That's a new angle. Is there weight to this? Well, yes, there is, but now the kid is riding on the sled, so that we have to combine their masses. And there will also be a normal force because there's contact between surfaces. Let's define a few things. The angle of the hill. Let's give this 27 degrees. Let's talk about the mass of the system. Total mass. Well, that's the mass of the sled plus mass of kid, right? And so let's just say, well, we got 5.1 kilograms. And a typical kid is, I don't know, let's give him 37.1 kilograms. So our total mass of the system is, no, I did that wrong. 37.1 is the answer. 32 kilograms for the kid. 37.1 kilograms is the total mass of the system. There we go. And, okay, I should draw a few forces, but then I'm going to resolve this into a true free body diagram. There's some weight to the whole thing. And check this out. There is a normal force. And the normal force, I have to draw it not vertical this time, but I have to draw it perpendicular to the surface. Aha. Normal force. I don't know how long to draw that arrow, by the way. I haven't worked that out yet. I can't assume anything. And it is perpendicular at right angles to the surface. I need a true free body diagram. And here's the first lesson. When the surface is inclined, then what you want to do is tilt your axes for your free body diagram to match. Let me do that here real quick. So I'm going to have an x-axis. Like that. I'm going to have a y-axis. Kind of like that. Y, x. Aha. There are advantages to doing this. You want to get in this habit. Okay, and I can show pretty easily that there's an angle, and I know that angle is 27 degrees. Okay. Forces. Weight is acting straight down, so I don't tilt the forces because I rotated my coordinate system. The forces are still acting in the same directions they're acting. Weight. I don't want to get too crazy with the lengths here. Still, weight's mg. That's still a thing right there. Normal force is perpendicular to the surface, so normal force is in the y direction, positive y direction. There's normal force. But let's figure out what's going on here. So, what about this? What if I figure out, first of all, sum of forces in the y direction? Well, I have the normal force in the y direction. Oh, but I also have, there's part of the weight in the y direction, and I need to work that out. I have to resolve that, and I didn't do that yet. So here's something that's really interesting. Draw the weight. It's about like that, right? Pardon me. Now, where are its x and y components? Well, its x component is along the x-axis. You can imagine doing this. And its y component is along the y-axis. I can imagine doing this. And the x and y components, those are perpendicular to each other, yes? So it sort of makes a rectangle overall. But my important question is, where will the 27-degree angle show up? Now, you can probably do this visually and simply say, well, that's easy. It's the smaller angle here. That's 27 degrees. That is actually correct. There's a great little diagram in your textbook that explains why this angle here turns into that angle there. If you don't see it, read up on that. But that's important because now this is my force component in the x direction. Here's my force component in the y direction. And look, the y component is now adjacent to the angle. Okay, so what are these forces in the y direction? Well, I know that they sum to 0 because I know the sled is not going to accelerate in this y direction at all. Not in this situation. So the forces are the normal force and the y component of the weight. Oh, I labeled this wrong, didn't I? Oops. Sorry, that's weight in the x direction, and that is weight in the y direction. Ooh, come on. Watch that now. So, I have normal force, and that's positive y direction, and I have weight in the y direction, which is in the negative direction, weight in the y direction. And those sum to 0. Okay. Can I figure out what this is? Well,
Mr. De Leon, please
watch
dial
this.
the operator. Mr. De Leon, please dial the operator.
I'm going to bring this over to the other side, but the weight in the y direction is going to be weight times cosine of 27 degrees. Can I figure out the weight? I can, because it's mg. So this is going to be mg times cosine of 27 degrees. All right. So what is this normal force now? Well, what is, I'm going to get 37.1. That's kilograms. And I'm going to get the 9.8, and that's meters per second squared. And I have cosine 27. For you calculus people that like your calculators in radians mode, this is where you want to go back to degrees mode. Please remember that. And you get a value for the normal force of 324 newtons. Okay, interesting, good, right? Why is it so much more? Well, we added the mass of the kid to the mass of the sled. And so it's to be expected it's going to be a lot more. Well, now, this is fine, but the thing isn't accelerating. The sled is not accelerating in the y direction. We expect, though, the reason the kid hauled it to the top of the hill is he wants to slide down. It's going to be fun. He's going to be accelerating in the x direction. There's possibly something unbalanced in the x direction, isn't there? Look at that guy right there. The component of weight in the x direction. So now we have to work that out. So one of those silly line things. And sum of forces in the x direction does not equal 0. You know what it equals? Mass times acceleration. I almost put g. It wouldn't be g. It would be the acceleration of this whole system in the x direction, right? But what are those forces in the x direction? It's only the weight in the x component of the weight. That's it. And I can figure that out. So that's ma. So what is this acceleration going to be? I'm going to divide by mass. Weight in the x direction is going to be weight which is mg, times sine of 27 degrees. So I have mg sine 27 degrees, but I'm dividing by mass. That's interesting. Equals acceleration. Look what happens here. Mass cancels out. Whoa, whoa. Wait a minute. You're telling me that the acceleration down the hill does not depend at all on the mass. And I'm going to tell you that's absolutely true. It depends on the acceleration due to gravity and the sine of the angle made with the horizontal. And that is it. And so we work that out and we get the, I'm going to show it down here. The acceleration that this child experiences on the sled is going to be rounding a little bit, maybe 4.45 meters per second squared. And so we found lots of stuff. Oh my goodness. We can find the value of the normal force because we know the weight, because we know mg. And the normal force is equal to the y component of the weight because it is zero acceleration. Sum of forces in the y direction is zero. But there is an unbalanced force in the x direction, the weight in the x direction, the x component. And this really interesting thing that mass doesn't matter. Independent of mass. Holy cow. So if I got my fat rear end on the sled, I would accelerate at the same rate as the kid. That's pretty cool. Sounds like fun. So a whole bunch going on. Guys, I want to recap what this video has been showing you. We saw a whole bunch of forces as vectors. We saw how normal force in an equilibrium situation, normal force will equal the weight as long as the surface is horizontal. We know what weight is, it's mg, and weight is really always going to be mg. But g can change if we're not talking about Earth, keep that in mind. We looked at inclined surfaces where things get kind of neat, kind of crazy, and there's unbalanced forces in the x direction, but in the y direction forces are balanced. And we saw a whole bunch of use of Newton's second law. And when we're doing this, we're always breaking up x and y components. We're treating this as vectors, looking at sum of forces in the x and sum of forces in the y direction. And we saw Newton's first law evident that it's going to stay there until an unbalanced force acts on it. And here we see an unbalanced force, and therefore it doesn't stay there. It accelerates.